two types of errors, which error is more acceptable in statistics? Okay, so yes, type 2 error is more acceptable. Okay, because it is better not to reject an HO, okay, when you don't have enough evidence, than rejecting the HO, but your results are actually not accurate. Okay, it's leading to a false positive. Okay, so not being able to reject an HO is better, okay, than rejecting it, but you don't have accurate results. Okay, so for number two, it says here enumerate and explain factors that lead to the occurrence of a type 1 error. Okay, so yesterday I think I mentioned this in the class that when there is garbage in, there is also garbage out, right? So in order for us to minimize the least possible errors, okay, we have to make sure that the data that we collect, okay, are reliable data, okay, so that the result will also be accurate. So, what happens if there is a type 1 error? It could also mean that some violations of assumptions of the statistical tools were made, and you really continued using on a certain tool, even if your data violated some of these assumptions. So, it could also lead to a type 1 error. Another factor there is also the sample size, okay, which you mentioned here in your answers. So, the bigger the sample size, the better it is for our results, okay, because it minimizes the type 1. Now, for the third question here, it says, how can type 1 and type 2 errors be minimized? Okay, so for type 1 error, you also mentioned here in some of the answers, we can minimize it by decreasing the significance level, okay, but you cannot minimize type 1 and type 2 errors at the same time, okay, because type 1 and type 2 errors are connected with each other. If you minimize the type 1, you increase the type 2. If you minimize the type 2, you increase the type 1 error. So that is the relationship between type 1 and type 2 errors. Now, of course, it is ideal to minimize the errors as much as possible, right? Like, for example, we can favor type 2 error over type 1 because we want, it's better, as what I've said, it's better not to reject a null hypothesis when the evidence is not enough, then rejecting it, but our data is not accurate. Okay. So if you reduce the statistical significance, okay, let's say from zero point zero 0.05, you decide to have it as zero point zero 0.01. So you reduce the type 1 error, right? In that case, you have also to bear in mind that if you do that, it is also difficult for you to get a significant result, okay, if you do that. Okay? So there are things that becomes a sacrifice when you reduce a certain type of error, you increase the rate. That's why researchers mostly use the zero point zero 0.05 because it creates balance between the type 1 error and type 2 error. So that is the thing. So if you lower the significance level for the type 1 error, it says the type 2 error. But it also increases the statistical power of your results. Okay? And another thing that can also increase statistical power is to increase your sample size. Okay, so these are the measures. Okay, so the others that did not post yet, one, six, I'm expecting 8 posts. You can catch up later and post, okay? But I will check it if you have posted already, so we can continue to the next part of the lesson. Okay, so let's proceed now to statistical tests that we are going to use in our course for this afternoon, for this morning. So we're going to focus more on the parametric tests, but let me discuss with you what parametric tests are and what non-parametric tests are. So in statistics, we decide on the tools that are most appropriate to our study, but we also try to navigate more towards parametric tests because they are tests hold more statistical power than non-parametric tests. Okay. So yesterday we discussed and learned about normal distribution data, right? And the particular assumption of a normally distributed data is the most common assumption that is being required in parametric tests. Okay? So parametric tests assumes normally distributed data, while the non-parametric tests assumes, or rather doesn't assume any distribution. Okay? That's why it's also called a distribution-free test. So I'll repeat, parametric tests are tests that assume a normally distributed data, but non-parametric tests, they do not assume any distribution, therefore it's called a distribution-free test. That's why usually if we violate one or two or three assumptions in the parametric test, we usually take the other option of using its counterpart in the non-parametric tests, because it doesn't assume these assumptions and it doesn't follow a normally distributed data. Now, when you compare a normally distributed data over a distribution-free data, okay, so what does it mean? For example, in the data that I showed you yesterday, we saw that there is a data that is not normally distributed, right? And we also saw another example that the data was normally distributed. So normally distributed means it follows the bell-shaped curve. And if it says distribution free, meaning it is immune to that type of assumption. It could be skewed to the right, skewed to the left, so on. It doesn't matter because it doesn't affect the results if you use a non-parametric test for that particular data. So in statistics or in mathematics, for example, if you try to look at a normally distributed data, we consider that a predictable data, okay, because we know how it looks like, right? But a distribution-free data is considered a non-predictable data. Now, in mathematics and statistics, the more predictable something is, the more power it holds. Okay, so that's why if we have tests that we are going to use with our data, it is advisable to try out the parametric tests first if our data passes the assumptions, because parametric tests holds more power than non-parametric tests. So this is the reason why we try to assess first. We try to eyeball our data and we try to see if our data passes the assumptions. Okay, not, let's choose the counterpart in non-parametric tests. So there are quite a number of parametric tests that are being used in statistics, but today we are going to focus on these three tests that you see on screen. And these are the Pearson's product moment correlation, independent samples t-test, one-way analysis of variance, or okay. Now, for ANOVA, when the results are significant, we conduct a follow-up test to know more information about the results. Okay, we call this the post-hoc tests. Okay, we have here, I'm going to explain to you later on about Tukey post-hoc test and the Gibbs-Howell post-hoc test. But I'll explain it more later when we reach the discussion about ANOVA. Okay, but first, let us look into Pearson product moment correlation test. Okay. So, what is a Pearson product moment correlation test? We sometimes call this the Pearson R correlation, okay, or the Pearson's correlation test. So, we use this to determine the strength of relationship, okay, or the direct relationship, okay, between two continuous variables. So R is denoted as the coefficient. So when we present our data about the Pearson product moment correlation, we denote that as the R, small letter R. Okay? So values range from -1 to +1, and 0 indicates no relationship. To be specific, -1 indicates a negative correlation, and then the positive there indicates a positive correlation. Okay? Now, correlation, it does not mean causation. Okay, what does it mean? When you say causation, it means that what happens to this variable cost the change of the other variable. That is causation. Okay. The other variable is the cause of the change of the other variable. But when you say correlation, it is not causation, okay? Because it only means there is a certain relationship between the two, but it doesn't necessarily mean that the change of the other is the cause of the other variable. Okay, so there is a limitation to Pearson moment correlation. This is not the same as regression analysis because there is also another tool we call the regression analysis, wherein it also looks at the correlation at the same time the causation of the two variables being two or more variables that are being analyzed. Okay? But for now, let's focus solely first on the correlation and later for the causation. Okay. Now, what does correlation mean? If we have a positive correlation, it means that the increase of one variable causes also that, okay, let's not use the word cause. Okay. The increase of one variable has also an increase of the other variable. Okay. But if there is a negative correlation, the increase of the other variable means the decrease of the other variable. There's an opposite flow there. And zero means there is no relationship between the two variables. Okay. So here are some examples. Determine the strength and direction of a linear relationship between salaries measured in US dollars and the length of employment in a firm measured in days. We want to see if there is a significant relationship between salaries and length of employment. In the second example, we want to see if there is a strength and direction of a linear relationship between reaction time measured in milliseconds and the hand grip strength measured in kilograms. Okay, so these are some examples wherein we can apply this particular statistical tool on Pearson product moment correlation. Now, for you to be able to relate more on this, I want to show you an example of a real data in SPSS, and then we try to look into the relationship between these two variables. But first, let's look at the interpretation of Pearson product moment correlation first. We have here a table that will tell us if the relationship is a strong relationship, is it a moderate relationship, weak relationship, and so on. Okay, let's look at this table under psychology. Okay, this because we are in that field. Okay, we are in politics or medicine. So we look into that column there. We can see there that there is a verbal interpretation on the different values of the R or the correlation coefficient. So for example, if okay, your value belongs between positive zero point 0.1 and negative zero point 0.1, then you can say that there is a weak correlation. If the value is positive, you will say weak positive correlation. If the value is negative, you say weak negative correlation. So, okay, so that is how you interpret the value of R. You look into the range given here from the table, and then you try to see if the relationship is strong, moderate, weak, and so on. Okay. You cannot have a perfect correlation, not unless, okay, you are trying to correlate the same variable. For example, you earlier there was an example, you want to see the correlation between salaries and uh, what was that? Time spent in the firm. Uh, salary and employment, length of employment in a firm. Okay, salary and length of employment in a firm. Now you want to see the relationship. But what if I want to correlate two variables such as the salary and the salary? Of course, you get a perfect correlation for that because it's the same data that you are trying to find the correlation, right? But usually we don't do that. We find out between two different variables, okay, and the values should range, okay, here, the same as what you see on the screen, okay. Eliminate the positive one and negative one and then the zero there, okay. You can see those values and you can interpret the value based on how strong the relationship is. Now, there are certain assumptions or requirements that we need to follow before we can use the Pearson correlation test. Okay, so these are the assumptions. The first one is continuous data. It means that the two variables that you are going to analyze should be measured on a continuous scale. Okay, remember yesterday we discussed about different types of data. And in SPSS, okay, there are three types that we can assign there: the nominal, the ordinal, and the scale data. Okay, so both variables should be in a scale data, continuous scale data. Another thing is paired values. So what does it mean when you say paired values? The two continuous variables should be paired, which means that each case, okay, example given, each participant has two values, one for each variable. For example, we want to see the correlation between salary and employment, length of employment. Okay. If I have 10 respondents, I need to have 10 data for salary and I need to have 10 data as well for the length of employment so that they are in pairs. Okay? Meaning, respondent 1 has a data on salary, has a data as well on length of employment. So we can have them all in pairs. Now, what happens if your data on one variable is not equal to the number of data in the other variable? Can we do Pearson correlation? The answer is no, because they are not anymore in pairs. Okay, this violates the assumption of paired value. So you cannot do that particular test. Okay? Or, for example, you want to look at okay, let's go back to the study on the readiness and performance of the intensive English course. Now, example, there are only 15 teachers involved in the study. And you have, yesterday there were like 1,000 something students, right, involved in the study. Now, I want to look at the readiness of teachers and the readiness of students and see if they are correlated. Can I do that? The answer is no. Why? I only have 15 data for teachers. I have 1,000 something data for students. I cannot put them in paired values. So that violates the assumption of Pearson correlation. Therefore, we cannot perform the correlation test for that. Okay? Not unless we have equal values of the data. Then they can be in pairs, then it passes the paired values assumption. So the next one is the linearity. So there needs to be a linear relationship between variables. Okay, how do we find out? If we have two variables, okay, let's say salary and the length of employment, we graph them in SPSS in a scatter plot, okay, with the X and Y axis. And we try to see the points or the values. If they fall closely to a straight line, then we consider the values to be linear, or there has to be a linear relationship between those two variables. If it doesn't fall closely to a line, then it violates this assumption. Then we cannot perform this particular test. The next one is the outlier. Remember yesterday we discussed about outliers and how to deal with outliers. Now it says here there should be no significant outliers. What does it mean? Those values yesterday that we saw that there were asterisks, right? And there are also values that are only like have the circles that they are outside they're also considered outliers, but they are not considered significant outliers because they don't have the asterisks. Okay. We only have to look at those values that has the asterisk in it. Okay, then that is considered as a significant outlier. If there are significant outliers, it will greatly affect the result of your data. So we have to do some measures with those outliers to be able to perform this test. And the next one, the last one, is the normality. So yesterday, I told you that normality is the most common requirement for statistical tests, especially for parametric tests. Okay. So we have to check if our data is normal. If not, if not normal, we have to check the sample size. If the sample size is 30 and above, then central limit theorem applies to that data, then we can neglect this assumption. Okay? We don't need to follow normality as long as your sample size is large. Okay? So if your data violate the assumptions of statistical techniques, such as the Pearson correlation, for example, to the non-parametric counterpart was the Sussman rank correlation. Okay? Let me show you how correlation looks like. Share my I want you to pay attention how we perform these three tests that I going to discuss to you this morning, the Pearson, um, independent t test, and the ANOVA, because later in the afternoon, I will put you into three groups, and I want you to try out performing these tests and interpret your own results. Okay? So please take a look.